All right, so now we just have to show that this inequality holds for some large enough n, right? So we'll see here in a little bit what n's gonna be, but you have to get a little bit creative. So because n factorial is positive, the first step that I did was I multiplied through by n factorial, and I ended up with negative n factorial over 2 to the n less than or equal to negative 1 to the n less than or equal to n factorial over 2 to the n. So effectively, I've just cleared out the denominator and the central term for c of n. Now what I'm going to do is I'm going to try to find the n that's going to make this work. So the way I do that is I kind of write out what this looks like in general. So this is negative 1 times 2 times 3 times 4 times 5 times 6, etc., and so on, all the way up to n. That's n factorial. And on the bottom, I have n copies of 2. So 2 times 2 times 2 times 2 times 2 times times 2. And there are n copies of 2, right? So this is multiplied together n times per the definition of 2 to the n. In the center, I change nothing. And on the right-hand side, I do very similar work. So 1 times 2 times 3 times 4 times 5 times 6 times all the way up to n. And then on the bottom, I have n copies of 2 multiplied together. So this is another n copies of 2 multiplied together. And what I'm going to do is I'm going to kind of pick out the first 4 terms. So we can see that once we get to the 5, 6, n, then that's really going to take off relative to just multiplying 2 together that many times. So I'm going to say this is negative 24 because this is my grouping. I'll show you how I'm thinking about this. So my grouping is to look at these 4 and these 4, these 4 and these 4, and then I'm going to separate that against these last n minus 4 terms. And I'm going to make a comparison here that will be helpful. So this is negative 24 times, instead of writing 1, 2, 3, 4 multiplied together, I write 24. Then I write 5 times 6 times all the way up to n. And on the bottom, I'm going to have 2 to the 4th times 2 to the n minus 4. And the thing to notice on the top, actually, maybe I'll move this down a scotch, is that there are n minus 4 terms here, right? So I have the first 4 and then the n minus 4 for a total of n minus 4 terms. And what happens is I'm going to do the same thing on the right-hand side as well, except that it's going to be just positive is really the only difference here. So I can go ahead and erase my negative sign. I'm going to draw my inequalities because I haven't changed the value of anything. And just to be clear, I'm still looking here and here. Here and here, and that's going to be the same breakdown on the right side as well. So the cool thing about 24 over 2 to the 4th, that's 24 over 16. So really what I get is if I take 24 divided by 16, I can write that as negative 1.5 times 5 times 6 times times n over 2 to the n minus 4. And in this fraction, there's n minus 4 terms on top, and there are n minus 4 terms on the bottom. And then on the right-hand side, I'm going to have 1.5 times 5 times 6 times all the way up to n over 2 to the n minus 4. So, something cool to notice. We're going to add an extra layer in between. So, because the numbers in the numerator, 5, 6, 7, 8, all the way up to n, each one of those terms is bigger than 2, right? 5 is bigger than 2, 6 is bigger than 2, 7 is bigger than 2, blah, blah, blah. So this fraction here is greater than 1, right? Because every term in the denominator is bigger than every term in the denominator. Sorry, every term in the numerator is bigger than every term in the denominator. And then similarly, this guy over here is bigger than 1 for the same reason. So if this is bigger than 1 and it's negative, then I can say this is less than or equal to negative 1.5 for sure, right? Because if I multiply negative 1.5 times a number bigger than 1, it would be even more negative. And similarly, I can put a 1.5 over here because on the far right, if I took 1.5 and multiplied it by a number bigger than 1, it definitely would be bigger than just 1.5. So now I've created this really, I'm hoping it's obvious inequality on the left and the right. And then we just need to kind of verify that the inner inequalities hold as well. So the most negative that negative 1 to the n can be is just negative 1. So it's always going to be the case that negative 1.5 is smaller than negative 1 to the n. And similarly, the biggest that negative 1 to the n can be is positive 1. And positive 1 is always less than positive 1.5. So this shows that our original inequality holds, and we really need to kind of figure out what does it hold for. Like, so if n was 3, it wouldn't be true, right? Because I'd have, like, let's look at if n was 3. We're going to find that it's true for 4 and above. But if n was 3, then you would have, what would you have? You would have, I'm going to go back to our original inequality here. This was the original inequality that we wanted to show. So we're just going to look at why it needs to be 4. I just want to show you the value right before 4. That's kind of our last stop of it not working. So if n was 3, we would have 3's everywhere. So 2 cubed, negative 1 cubed, 3 factorial, 2 cubed. And you'd have negative 1/8 is less than or equal to negative 1 over 6, so that's already wrong, is less than or equal to 1 over 8. So negative 1/8 is not less than negative 1/6. So if n's 3, and clearly if n was smaller as well, we wouldn't get the inequality holding, but as soon as n hits 4, we get that top-heavy numerator, and so everything works out for us. So we showed that the inequality holds for whenever n is at least 4. So therefore, because we squoze C of n between A of n and B of n for some large enough n, we have demonstrated enough to assert that the limit as n goes to infinity of c of n also equals 0, right? So again, a of n had a limit of 0, b of n had a limit of 0. We showed that c of n was always tucked in between a of n and b of n whenever n was larger or equal to 4. And so therefore it follows that c of n also has to have the same limit as a and b. Okay, so now here's the part where you get really mad at me, because there's also this other theorem, the absolute value theorem. So if you have a sequence a of n, if the absolute value, if its limit is L, then, or sorry, if its limit is 0, then the limit of the regular guy is also 0. So for example, consider the example we just did, where we had c of n equaling -1 to the n over n factorial, then the limit as n goes to infinity of the absolute value of c of n would be the limit as n goes to infinity. So the only thing that changes is that the -1 will just be positive regardless of n. So this is just 1 over n factorial, and that equals 0. So I feel like I'm spelling therefore wrong, but okay. So therefore, the limit as n goes to infinity of regular old c of n equals 0, 2. Ta-da, that's it. So those are two things that you can use. The squeeze theorem is super fun if you like that kind of stuff. The absolute value theorem is really useful when you have a limit that is 0. So good luck. Please email if you have any questions.